So I'm going to remind you what we were doing last time. We were trying to prove the existence of an eigenvector, non-trivial eigenvector, in fact, a non-zero eigenvalue for Hilbert-Schmidt, self-adjoint Hilbert-Schmidt operators, which generalizes the fact that symmetric matrices or Hermitian matrices or the complex numbers always have a non-zero real eigen. Well, it has to be real if they're self-adjoint. So generalizes the fact and gives an alternative proof, not using minimal polynomials or whatever you use in the, I don't remember any linear algebra anymore. So.
It's more similar to you have proof you can do in like calculus 3 course, like in figurametry. You look at the same function where A is an operator matrix in a finite dimensional space, and you look at the minimum on the unit sphere. It's exactly.
So this. So I didn't know that they give it
the maximum.
So this is. This quotient is called the Rayleigh quotient. So let me remember what we did, how we were building up to this theorem. One, we already did. We defined what weak convergence is, or weak star convergence, and after we discussed if it's weak or weak star, there was also another discussion about weak and weak star in the free group seminar, right? So I'll keep the star. I don't know, but you all remember what it means. It just means you converge on any linear functional, right? So the evaluation of any linear functional, the vector converges, which just means inner product with any vector converges. Okay. Then we had definition of Hilbert-Schmidt operators, right? And we said that Hilbert-Schmidt operator, say A, restricted to the unit ball, but of course I can replace unit ball here by any finite radius, is continuous. Continuous, continuous what? Continuous from weak convergence to, or weak star, it doesn't matter, to norm convergence. Okay, so if you have a weak converging sequence that's all sitting inside the unit ball, then the image under A converges in norm, the correct limit. Okay? Now, it is true what Gal remarked last time, that I checked it. So it is true that weak converging sequences are norm bounded. So I don't need this assumption that they all live in the unit ball. We only use it to bound the norm between un minus u in norm, right? So we needed some uniform bound on that. But that proof requires a deep theorem in Banach space theory or Hilbert space theory.
So something we learn in modern analysis.
So you need uniform boundedness principle. Exactly. You need the uniform boundedness principle. This is not a trivial theorem. This is not a trivial theorem. I wouldn't want to put it in my book, for example. I mean, it's too much. I mean, I could use it and put it and assume, but it's like one of those theorems that I cannot guarantee you know when you did your undergrad studies, okay? If you did, I don't know, computer science math, then maybe you didn't take the course and something like that, so.
You know, it means that, it's a continuous from weak star to without extension.
Any Hilbert-Schmidt operator is, this is true, that any Hilbert-Schmidt operator is continuous from the weak star to norm. But for our purposes, we're going to work with sequences sitting inside some fixed radius, unit radius maybe. So it's enough to just look at it as a restricted operator on the unit ball. I mean, you can look at this, right, subspace topology. And so then this is all I need. And then we proved it. Then we gave a complete proof, isolated proof, without using any uniform boundedness principle or anything. Okay. 3, we defined this function. So I'll just define, okay, let's maybe give it a name. Okay, so we defined the function phi. Phi is going to be a function defined on all vectors, and it's just this, for some, let's at the moment just say some operator. It will be Hilbert-Schmidt, of course, at some point. But at the moment, I didn't even assume anything about this operator. This is called a, no, sorry. So I am assuming that A is Hilbert-Schmidt. Okay. Okay. So this was the notation for Hilbert-Schmidt operators, right? I am assuming that A is Hilbert-Schmidt. this function, so where is this? This is a function from vectors from Hilbert space to complex numbers, right? I didn't say self-adjoint. This has a maximum, so yes, I cannot talk about maximum. Okay, so A is self-adjoint. Otherwise, I would have to work with absolute values or something, but this has a maximum. So this is maximized on the unit ball, or any ball of any radius, of course. Okay, this is the maximum unit ball. This is just continuity. This is just continuity of a continuous function on a compact. So
how do you know it's maximized on the boundary? Does this have something to do with the maximum modulus or something?
So I don't know that it's maximized. I mean, I didn't prove that it's maximized on the boundary. I just said that there is a maximal, there is a vector attaining the supremum.
Oh, unit ball, sorry.
Okay. So there is a vector attaining the supremum. Necessarily, this vector is non-zero. Okay. And necessarily, this vector is non-zero. So I mean, it cannot be.
Yeah, I thought you meant unit sphere.
So this is that's all right. It's maximized on the unit ball, and this is basically just continuity. It's using the fact that the unit ball is compact. Okay, so this is using the fact that unit ball is weak star compact. This is Banach-Haloglu, okay? This will become a continuous function on a compact, continuous functions on compact.
It should be on the sphere just because if you multiply by alpha, like you take something on the sphere and you multiply.
I'm not even going to go into the discussion of that. Now, what we did is we took this function. Okay, we took this function and we defined what's called the Rayleigh quotient. This is an important concept that comes up many times in physics. Rayleigh was a physicist. So the Rayleigh quotient is what you define this way, defined to be phi of u divided by u squared. This is homogeneous. Homogeneous meaning if you multiply the vector by a scalar, the scalar, it gives the same value, right? Because here you get the scalar squared, here you get the scalar squared, so, okay, this is homogeneous, but it's defined only for u not equal to 0, right? So this is where I need to, otherwise I have a problem defining it, okay? I will have to give a separate definition for u equals 0, okay? So this is not defined in a neighborhood of 0, or not defined at 0, actually, right? And then what we notice is that if V is W normalized, where W is a maximizer of phi in the unit ball, you see, I didn't assume that W has unit length. Just some vector, non-zero vector that's maximizing my bilinear form here. Then if I take the normalized version of W, then psi of V, we did the calculation, is going to be a maximum of psi. Okay, so psi of V, so for any unit norm U, which is non-zero, so anything which is not 0 but is of unit length, sorry, at most unit length, okay? So anything in the unit ball minus 0 where I can talk about psi of V is going to be psi of W, which is what? Which is yeah. So this is by definition phi of W over W squared. Now this is the maximum in the unit ball, and this is less than or equal to 1. This is always greater or equal to phi of U, okay, and this thing.
Who is the maximized, the W or V?
W. Yes.
It's greater than phi of W.
So yeah. So psi of W is the maximizer of phi. V is the normalized version of W. This is why the psi's are equal. Psi of W is equal, by definition, to phi of W divided by W squared. This is greater or equal to phi of U divided by U norm. Why is this true? This is a unit non-zero unit vector, okay? And so this is bigger than this, and this is at most 1. Okay, just the norm of W is at most 1. So everything lives in the unit ball. Okay, so this is bigger than this. This, because this is a unit vector, is equal to psi of the same thing. But psi is homogeneous, so this is psi of u. Okay. Always get mixed up in this calculation, but anyway. So the normalized version of W is a maximizer for the Rayleigh quotient. This is just a consequence of this normalization and homogeneity. I mean, it's what you do. Okay. And this is the point where we're at. And remember what we're trying to prove. We're proving theorem. If A is a self-adjoint Hilbert-Schmidt operator, then there exists a non-zero lambda, non-zero V, of course, such that AV is lambda V. Okay, this is a scalar. And in fact, lambda will be real because of self-adjointness. Okay, so this is what we're proving. Okay. And so let's go into the proof using this, all of the machinery we developed so far. Okay, the machinery developed so far. Fix V of norm 1, which maximizes psi in the unit ball. Unit ball, I mean, without 0. Okay, because psi is not defined on 0. Okay, so you fixed our V, which is the same V that I wrote down on the left side. And then fix any U and H, okay, any vector, and consider the function P, which is P of U. This is going to be a function from R to the complex numbers, into the real numbers, but it's not so important in the moment. Okay, so P of a real number is going to be, this is P of U. It depends on U, it depends also on V. So we can write V and U. They don't play the same role, so you have to be careful. U is any vector, V is a specific vector. I mean, right? So but let's do this choice. And what the real number that you get is just psi of V plus R times U. So you just move away from V in the direction of U. Like the line going through V, right? In the direction of U. Okay. So you see that actually U is not important. I could have chosen U to be a unit vector, right? It's only the direction of U which is important. Okay. But we'll keep it just for thing. And of course, this is constant if U is 0. So I could also define it for the 0 vector. It's not so. I fixed some function, right? So this is a function R to C. In fact, you can see that this is real value. So it's okay. Now, the previous considerations that we wrote on the board. What they tell us is that this function has a maximum, a local maximum at some point, right? So 0 in R is a local maximum of P. Okay? So first of all, this is not defined everywhere. This is not defined for all R. This is only defined in the neighborhood of 0. Okay? This is only defined in the neighborhood of 0. So this is defined in neighborhood. It's not an honest to goodness function. On R, I need to tell you what happens if this happens to 0. This happens to, if U happens to be a multiple of V and R is exactly the right number, then this is not defined. So there's one point that I need to be careful of in some cases. In some cases, I mean, if you use in a different direction, then I have no problem, right? Okay. So defined in the neighborhood of, but it's always defined in the neighborhood of 0 in R. And 0 is a local maximum. Okay. There is some small enough epsilon such that this is defined in minus epsilon epsilon, and 0 is maximum on this interval minus epsilon epsilon, right? That's what the previous considerations tell us, because V is the maximum. Okay. So what can you do? We take derivatives and compare it to 0, right? So what is the derivative DDR of the form some operator acting on V plus RU, V plus RU? Right? What is this derivative? Well, let's write out what this function says. This function says the following. It says TBV, right? Plus, I have RU, so I get R squared TUU. Okay? These are just some complex numbers, and that's R squared. And then I also have R times V, R times, what is it? I get TVU plus TUV, right? So. Okay, so it's just a degree 2 polynomial in R. So it's very easy to take derivatives, okay, right? And so I can take the derivative, and what I get here, if I compute the derivative of such a binary form.
Is the normalized, isn't it?
Yeah, but I'm first taking a derivative of such a thing, and then I have a quotient of two such things with different t. One time it's the identity, one time it's A. So when I take the derivative of this thing, what do I get? I'm left with this term and this term, right, with the 2R, and this term disappears because it's constant in R. So what I get is 2R TUU. T is just any operator, any operator.
And then we will use it for A.
Other operators. Now I'll use it once t equals A, once t equals the identity. So it's 2R plus a constant, which is TVU plus TUV. Okay, this is the derivative, right? Now, so now when I take derivative at 0 of P, this should be 0, right? Because 0 is a local maximum, okay? So derivative at 0 of P is what? So I have a derivative of the top, which is of the form A, V plus RU, V plus RU, right? That's the top, divided by V plus RU with V plus RU inner product, right? So if I use on the top t equals A and on the bottom t equals identity, I can take the derivative of a quotient, right? So it's just a derivative at 0, right? So what do I get? When I do the derivative of a quotient, I need to do the top derivative times the bottom without derivative minus the opposite and divide by the bottom squared, right?
0, yeah.
I'm taking the derivative at 0.
No,
0 is a local maximum, so the derivative has to be 0. That's that's why I'm doing this computation, right? So so if you do the right, so I have the derivative of the top. The derivative of the top is where t equals A at the point 0. At the point 0, this thing disappears, right? When R equals 0, and you're only left with this thing. So I get an AVU plus AUV, but A is self-adjoint, right? So AVU plus AUV is 2 times real part of AVU. Okay, that's AVU plus AUV. This has to be multiplied by the bottom without taking derivatives, right? But then it's 0. But then it's right at 0. What is the bottom without taking derivatives? It's V plus RU norm squared. When R equals 0, that's just norm V squared, which is 1. Okay.
Once again, please.
I'm doing, okay, let me write it. Do 2 steps. So how do I take derivatives of this thing? At R equals 0. First, I take the derivative of A V plus RU, V plus RU, so this is, think of T equals A, times V plus RU norm squared. So the second one, I don't do any derivative, okay? Then I have to subtract A, V plus RU, V plus RU, times this thing derivative. So the derivative of V plus RU, V plus RU, okay? All of this divided by V plus RU norm squared. Okay, this is how you take derivatives of real functions. So, there's no, okay, and all of this at r equals 0. Now I check what are these things. What is this at r equals 0? It's a derivative. What is it at r equals 0? It's this thing falls away, and I have AVU plus AUV. A is self-adjoint, so it's just AVU plus complex conjugate AVU, which is 2 times real part AVU. So I have 2 times real part AVU. Okay? Then I have V plus RU, when R equals 0 is V squared. V has norm 1. We chose V to be norm 1. So this is just 1. Okay? Minus. Now we have A, V plus RU, V plus RU at R equals 0. This is AVV. Okay? Times what? Times the derivative of this thing. So this is just T equals identity at R equals 0. Again, this drops. At R equals 0, T is the identity. Then I have VU plus UV. VU plus UV is 2 times real part VU. Okay? Good. Divided by V plus RU when R equals 0 is just norm V. Squared is to the power 4. It doesn't really matter. This is 1, right? So I get this equation, and this has to equal 0. So it gives me an equality. For which U does this hold?
AV.
Every U. Every U, right? We did this computation for a fixed U, and it's true for this is equal to 0 for fixed U. For every U, no R involved anymore, right? Because we substituted 0. Okay? So we conclude, erase all of this, we conclude that the real part, let me rewrite set lambda to be AVV. This is a non-zero thing because remember V maximizes something here, right? It cannot be 0. And it's of course real because A is self-adjoint, okay? And then we look at that for every U in H, we get that, okay, so what does this say? So this says real part, the 2's disappear because this is equal to 0, and it says this real part is equal to lambda times this real part. Okay, so we get the real part of AV U is equal to lambda times the real part of VU.
This implies that AV is lambda V.
Yes, and this is for every U in H, right? So I can also do this for IU, right? I can take U and multiply it by I, right? If I take U and multiply it by I, the I comes out minus I here, okay, and minus I here. Real part of minus I times a complex number is imaginary part of that number. So in fact, we also get that this is true for the imaginary part. Lambda is a real number. And so okay, this is just for free because it's true for every U. And if you add these things, you get that AV minus V, inner product with U, is equal to 0 for every U in H, which means that AV is equal to lambda. Okay, right? Good proof.
We had already cool. This is cooler.
This is just the proof is cool.
It was the cool inequality, you know?
Yeah, that is cool.
This is
This is the cool equality.
this was an adjective. It's not a name.
It was cool. And beyond that, you know.
So what do we do? What do we do with these things? So what we do with these things is very interesting.
This is like all of we done here is like an exercise or a theory like analysis or model like something like that.
And it's basically linear algebra. It's basically how you would prove that the self-adjoint operator has a real eigenvalue.
Because we saw in Yair's also Hilbert Schmidt, and he just like wanted, okay, now we have eigen value and eigen space, and that's
It's clear.
yeah. Now I believe.
Okay, so recall that we have an action of G on H, which is unitary operators. And this gives us an action of G on the Hilbert-Schmidt space by conjugation. And it's not true that a unitary operator is a Hilbert-Schmidt operator. In fact, it's probably a very non-typical case. But a unitary conjugation of a Hilbert-Schmidt operator by a unitary operator is again a Hilbert-Schmidt operator. And in fact, this preserves the inner product, so it's the unitary action on the Hilbert-Schmidt. And I'm reminding you how do we, what does conjugation look like? We can ask what the conjugation of a basic tensor in the Hilbert-Schmidt space looks like. This is just, you can act on V and then take its tensor with the action on U. Okay? So here you first act, then you take tensors. Here you first take tensors and then you act in the Hilbert-Schmidt space. And I'm reminding you that V cross U, the way this acts on W is you, I have to remember, this is bracket, so it's WV U. Okay? And so that's how the operator is defined. Good. And now what do we do with this? So the first thing I want to say is that
What do you mean by sorry, I'm sure we saw it, but the tensor on the sorry. Okay, sorry.
this is the definition of the tensor.
No.
I mean, in general, the conjugation is just by conjugation, composition of operators, but I just showed you that it works nicely with the primitive tensors, with the tensors that you have a vector. Not every operator in the Hilbert-Schmidt space is a tensor. It's a linear combination of such things because of you can take an orthonormal basis and the tensors will form an orthonormal basis. Okay, and now I want to prove the following theorem.
Also limits or it's only linear combination of such
If you have an orthonormal basis, then it's also well, yeah, you have to take limits.
It's not only every operator or
It's for a the space spanned by an orthonormal basis is dense in the limit. Okay. So assume that there exists a non-zero Hilbert-Schmidt operator, not assuming it's self-adjoint, such that L is fixed by G. Okay? A fixed vector in the Hilbert-Schmidt space, so it's already in one more level up. Okay? Then there exists a subspace of H. Okay? The subspace is non-trivial. But finite dimensional. Non-trivial subspace, but finite dimensional. Okay? Such that it's G invariant. Any vector in V is mapped by G. Now this is the action where? This is the action below, not in the Hilbert-Schmidt. This is already the action, the original representation. Somehow fixed points in the Hilbert-Schmidt space give you fixed points, give you finite dimensional subspaces in the original unitary presentation. And let me add one more thing that I will need. Moreover, there exists a non-zero V and V such that LV is not zero. Well, there exists V and V such that LV is not zero.
Like this is not just the kernel of the extra thing.
Yeah, I mean, I don't know why the kernel would the kernel is always be finite dimensional. I mean, that's already
No,
already finding a finite dimensional invariant subspace. What does this mean? This means G acts on a finite dimensional vector space. This means G has a homomorphism which goes into GLV or GLDC. Right? That's already telling you that G has a quotient, which is a linear group. That's a lot of information. Linear groups have a lot of structure. It's already a ring. It's not just. I mean, it's a ring. It's a Banach space. It has a lot of structure. Right? Banach algebra. I don't know, C star, whatever you want. Okay, so let's prove this theorem. Who's the subspace going to be? Well, first of all, the subspace is going to be the space of the eigenspace of a certain eigenvalue, non-zero eigenvalue, but we don't have a guarantee that we have an eigenspace for a non-self-adjoint operator. I didn't assume that L is self-adjoint, but I want you to know.
it's not L.
Yes, I want you to know that XL star X minus 1 is L star.
We are now in the proof of this theorem.
Yes, we are proving this. Okay, so XL star X minus 1 is L star because this just reverses the right. So you still get, so L star is, if L is a fixed point, L star is also a fixed point. And then you define A to be 1/2 L plus L star. Symmetrize L and you get, this is the Hermitian part of L. The anti-Hermitian part, right? You can do it. And again, you think of this as the real part of L, and there's the imaginary part of L. Okay, so A is now, so A is a self-adjoint Schmidt, right? And so there exists non-zero lambda and V such that AV is lambda V, right? And so we can take V to be the space of all V in H, such that AV is lambda V for this lambda. So this is the eigenspace of lambda, right? And this is a vector space. You can check that this is a vector space. And it's non-trivial because that's what the theorem told us, that we have a non-trivial eigenvector. Okay, so it's not just zero. And V is not zero.
Maybe it's a word, but it's not. We said that L is 0, but it's the same.
We'll see. Okay, you want to say why L is not zero on some vector in this space? I still need to prove the space is finite dimensional.
Yeah, you said
and that it's invariant. We'll see in a second. Okay, this is the space now. Now to prove the properties is just an exercise. But okay, so first of all, for this V, it takes this V and V, doesn't matter which one, right? And you write LV. Okay.
But you don't know this space is going to be finite dimensional, right? Maybe you can take a finite dimensional subspace. But you necessarily know
This
this.
is going to be a finite dimension. I'm going to show you that it's finite dimension. Okay, but we start with yeah, we want to, so because of Nadav, we were going to start proving this one first. Okay, so we take this V.
We also need to know that A itself is not zero.
If we will show
Okay, if A is zero, then L is zero.
But what if L is
If L
It would be that L equals minus L star, anti-symmetric.
saying if L equals, L is anti-symmetric.
Doesn't the same work, doesn't the same proof as before work? Because then you get the imaginary part of. replace, אם נחליף אופרטור שהוא צמוד לעצמו, אופרטור ששווה למינוס ה-R שלו. וכל ההוכחה
לא, אני רק אומר ש-A...
כן, כן, לא, אני אומר אפילו מקודם, אם ההוכחה הייתה עובדת, ואתה יודע להגיד שגם לאופרטור כזה יש כבר.
שאלה אם אנחנו משתמשים בזה
אני משתמש בזה כדי להגיד בסוף על ה-real part. אבל תחליף את זה ב-imaginary part.
יכול להיות שזה עובד גם, אבל הנקודה היא...
Okay, you're right. I have to be careful. This is a mistake. So I can take A to be this, or A to be, and you think I times I over 2 times L minus L star, right? So if L is minus L star, this one will be 0, but then this one will be not 0, and this should be self-adjoint. Right? Because when I star this, then the I becomes a minus I, and this minus flips.
This is the decomposition of
Right?
every.
It's exactly the decomposition. So what you're saying is, what if you have a purely imaginary one? That's correct, and the real part is 0. So then I need to take this. Okay, but one of them is going to be a non-zero self-adjoint. That's the thing, and you're completely right, and it's just wrong in the book.
The usual thing you do when you want to get self-adjoint or even a positive operator is take L star L. But
No, I want a linear thing here. I don't want a composition.
This might be not in Hilbert Schmidt.
I don't want to compose them. I want a linear combination. The half is not important. But okay, one of these you agree has to be a self-adjoint non-zero operator, right? Right? They're both self-adjoint, but one of them at least has to be non-zero. If both of them are 0, it means that L is 0. Okay? Because their sum is now for any V and V, if I look at the real part of LVV, what is this? Well, it's just this plus its complex conjugate, and you can take the complex conjugate, it's L star, right? So you get L plus L star. So 2 times the real part would be L plus L star. So you get LVV plus L star VV divided by 2. And this is L plus L star divided by 2, and this is so without loss of generality, let's work with this one, and you can do the exact computation for the other one. Okay?
Yeah, if it has 0, we will show for him the imaginary.
So this becomes AVV, right? Which is lambda norm V squared. And if you just take a non-zero V in this thing, then this is not 0. And so L there is a vector in V, so that you can, L acting on it, inner product with itself, is going to be non-zero, right? So it cannot be so LV cannot be 0. And if it was the, so I can write it. If I did the imaginary part of this thing, then what I would get is not the A. Okay, so we can call this A tilde just in case we want to differentiate them. What we would get here, we would get an A tilde VV, right? Which would be a lambda V squared in the tilde case. So one of these would be non-zero, depending if we're working with A or A tilde. Okay? Depending on which one we wanted to use here. Okay. Which means LV cannot be 0. Okay, so that's the first property. Now we want to show that the dimension is finite. Dimension is finite. Right? We want to know dimension is finite and that it's an invariant space. So first of all, any eigenspace is an invariant space because of the unitary action. So if V is in V, and I act on XV, right? Then how do I determine if XV is in V? I have to apply A to it. So if I apply A, this thing, right? Okay, then what do I get? I get that AXV, well, this is X acting on X minus 1 AXV, right? But X minus 1 AX is A. And this would also be true if it was tilde, right? Both of these are invariant under applying x's because the L's are invariant under applying x's and they're linear operators. So what I get is that this is equal to, this just becomes an A, and I took a vector which is an eigenvector, so I get x acting on lambda v, right? So this is lambda times x acting on.
What did we do? We take X and how did?
I took any v and any x. I acted on x on v with x and showed that xv is also an eigenvector. Xv is also an eigenvector. This any eigenvector, the space is the space of eigenvectors, so they all go inside. Okay. So this means that for any v in v, xv is also in v. This is invariance, so. Okay, and it would be true if I did the tilde. This has not, the only thing I needed the tilde for was to say that one of them was non-zero. The rest of the computation doesn't care about.
You say here that if you have if you have two commuting operators, and an eigenvector for one of them is also an eigenvector for the other, because saying that XL X inverse or X inverse L X or A.
Saying that L is a fixed point for X implies that A and A tilde commute with any X. Okay? But you have to slightly be careful because what are you acting with? And I mean, so AX is not a Hilbert-Schmidt operator. So they commute as bounded operators. Within a pure space. Yes.
Finite dimension is it exactly because of Hilbert-Schmidt? Because
Now we need to use the Hilbert-Schmidt. We didn't use the Hilbert-Schmidt in any place here, right?
yeah, if it wouldn't be, then we take just an orthogonal basis, and then it's all sum of lambda.
Yes.
The
And so this is not true for a general operator. It's true for compact operators, but Hilbert-Schmidt specifically, it's easy to show. So finite dimensionality. So let B1, Bn be orthonormal vectors in V. So I take any n orthonormal vectors, okay? Then what do we have? And we can complete these to an orthonormal basis. And remember, what is the Hilbert-Schmidt norm? And again, if I did A or A tilde, it doesn't matter what I'm doing here, right? The Hilbert-Schmidt norm of A squared, this is the sum of all of the norms squared of the A acting on some orthonormal basis. So this is greater or equal just to summing over part of an orthonormal basis, which is this. Right? So this is always less than or equal to the Hilbert-Schmidt norm. Again, think of matrices. You have an infinite matrix. You know that if you sum all of the coordinates squared, this is finite. So definitely if you sum some of them, it's less than or equal to that. Okay? But this is BJ. These came from V. So they're all eigenvectors with eigenvalue lambda. So this is exactly equal to the sum J equals 1 to n of lambda BJ norm squared, which is, this is 1, this is lambda, so I get lambda times n. I have a bound on n in terms of lambda and the Hilbert-Schmidt operator. Okay? So n is less than or equal to the Hilbert-Schmidt norm squared divided by lambda. But this is fixed, so I cannot make n go to infinity. That's it. Maximum orthonormal set in V is going to be of size at most this thing.
You also know that if you have a compact operator, for example, Hilbert-Schmidt operator, you can take its restriction to the eigenspace, right? It still has to be an Hilbert-Schmidt operator.
Mm-hmm.
But the restriction is just given by multiplication by a scalar, right, by lambda.
Okay.
So either lambda is 0, for which the eigenspace can be not dimensional, right? Lambda is 0, you can have infinite dimensional.
exactly by the formula.
Yeah.
Yes, but
Gives no bound. Yes.
if lambda is a non-zero scalar, you can't have multiplication operator being compact unless it's finite dimensional space.
Typically, that's what a Hilbert-Schmidt operator does, right? It kind of takes an orthonormal basis, does some matrix on some finite dimensional space, right? And then it kills the rest of them. A lot of them will have infinite kernels, infinite dimensional kernels, but the eigenspaces will always have to be finite dimensional.
They all Hilbert-Schmidt operators are compact?
Yes, every Hilbert-Schmidt operator is compact, whatever that means. I mean, basically we showed, right, that the,
Operator is
we showed that it's
limit
continuous from weak
to finite
star
rank.
to.
limit of finite rank.
Yeah.
This is what it is, אוקיי.
בקיצור, לא נדבר על זה משום מה, אבל זה
לא, וגם,
כן, אני-
ואתמול בהרצאה של יאיר ביום ראשון פשוט נאמר כאילו, על ימין ועל שמאל, וזה קומפקט אופרייטור, זהו כאילו, אני כזה.
He's using Hill, I didn't know that you needed all this Hilbert-Schmidt.
קומפקט אופרייטור פשוט שולח, אם אני לא טועה, סדרות, שולח את כדור היחידה לקבוצה חסומה. שזה...
Okay,
שזה שחוט.
so now we're going to prove Ozawa's theorem.
קומפקט.
Now we're going to prove Ozawa's theorem,
סימן זה לא מספיק.
okay? I'm not going to remind you what Ozawa's theorem is. We're not going to prove Ozawa's theorem now. We're going to prove Ozawa's theorem
Why not reminding us?
at 11:15. Because we'll do the discussion, we'll develop the theory, we'll see how it pops out, the theorem pops out of actually analyzing what's going on, okay? So let's meet in 10 minutes.
יש דרך, אני אגיד מה...
So where are we now? Okay, where are we now? What do we have? Let's say different color. Summary of the situation. We saw that we have a group acting on the Hilbert space. In fact, it's even separable. This is a unitary action. This provides us with a unitary action on the Hilbert-Schmidt operators. Okay, we know that we have a cocycle, which is mu harmonic.
We start with an H or we already have an H?
No, we get the H from the theorem, which gives us the mu harmonic cocycle. Not every H affords a mu harmonic cocycle. I wish it would, but it's not true. We had to change our presentation on L2 in order to get, so we had to get a different space in a sense. Or a different homomorphism into that space. I mean, it's a different representation. You could always do it. If it's separable, you could always do it on L2. They're all the same. But yeah, I mean, you could push the homomorphism, the representation through the isomorphism to the Hilbert space. Okay, so we have a mu harmonic cocycle. Mu is, remember, mu is SA. We'll do G2 because we need to talk about variances. That's what's good for you in G1. And okay, so and now we also just proved using the fact that every so any fixed point in the Hilbert-Schmidt space provides, what did we just prove? That any fixed point provides a non-trivial finite dimensional subspace. Right? If we take something, we symmetrize it, get a non-trivial finite dimension.
So the only action we consider on G on H star plus H is by conjugation.
Yeah. This is the canonical action. I mean, I don't know of any other representation. You can, of course, lift this to H star cross H star. Now you have a unitary action on a Hilbert space. You can lift it to a unitary action on the next
Does
tensor.
that mean you don't think of just from one side, action from one side or the other? You think about
There's no
conjugation.
action on one side and the other because if you compose a unitary operator with a Hilbert-Schmidt operator, you do not necessarily have a Hilbert-Schmidt operator.
Not only subspace, but invariant subspace.
that is important. Finite dimensional invariant, G invariant. Good. Now, what I want to do is explore what happens when I'm in this situation. So this is a situation, 2017, I guess, it's, or maybe beginning of 2018. I don't remember when the paper came out. Ozawa is sitting in his house, right? And thinking about, but he has all of this in his head. Right? This is what he has. Now, probably the way I'm going to think about it is not the way Ozawa thought about it, because Ozawa is a functional analysis person and he didn't write it this way. But you can imagine, I mean, so this is like the Hollywood version of Ozawa's story. Okay, so it's like that. Make it change the truth so that it'll be a bit more suspense or dramatic or something. So if I fix some v in my Hilbert space, I can always look at the function hv of x is c of x inner product with v. Right? This we saw, this is going to be a Lipschitz harmonic function. Okay, this is always a Lipschitz harmonic function. And in fact, that's how we prove that there is always at least one non-constant Lipschitz harmonic function. Okay, and so
It is true for every V, like without demanding anything.
yeah. Right. Yeah.
No,
we
because,
prove this.
Yeah, okay. No, I didn't remember if we proved for any V, but
I
then
mean, you can see immediately that it's harmonic just by using the harmonicity of C. It's
Yeah.
linear, right? And I mean, it could be zero for some V's. C could happen to be orthogonal to some vectors, but you can always find at least one V where C is a non-trivial cocycle. So you can always find at least one V for which is.
for example, C of X.
But this being a Lipschitz harmonic function means that I can look at the Cool inequality, right? So, and as I said to Nadav during the break, what you do now is you have a Lipschitz harmonic function. Well, so you just start playing around with, you just apply everything you know about harmonic functions to these functions and see what happens, right? I mean, that's how you would play this game. Remember, you're a functional analysis guy, so you have in your mind that in the Hilbert-Schmidt space, I can find the finite dimensional subspaces from invariant vectors in the Hilbert-Schmidt space. You have this in your head. So I look at this thing, and I look at this thing, right, and I can take this. So what does the Cool inequality tell us? It tells if I do this, right, starting from x, right, this is, I'm reminding you what the Cool inequality tells for any harmonic function, and specifically for this harmonic function. Well, this squared is going to be less than or equal to 4 times the variance starting from x of hv xt, this is for any t, times the entropy difference. Okay? This is exactly what we proved in the Cool inequality. If you don't remember, just any harmonic function, this is true. The only reason I'm taking mu to have psi finite second moment is so that the right-hand side here is well defined. I have a Lipschitz function, it grows linearly, so if I have finite second moment, I can talk about variances because they converge. Good. Then I remember something. So first of all, so you see, now there are 2 things to analyze. This entropy difference in some group, right? And this variance. What does it look like? Okay, so let's start with the variance. Have the explicit form of the function. So let's write, what is the variance? HVXT. We have the freedom of choosing T on the right-hand side, so maybe we can play around with these things. We know what this decreases to. This decreases to the random walk entropy. So in the groups we're going to be considering, this is going to be 0. Going to decrease to 0. So this is decreasing to 0, and this is typically increasing, right? I mean, you go farther away, you get a bigger function, right? I mean, that's how functions sense. It should happen. I mean, at least in absolute value, they should get bigger and bigger, right? We didn't talk about the maximum principle, but harmonic functions get maxima and minima on the boundaries. So if you take absolute values, it's going to be bigger and bigger, unless it was bounded. This one is definitely not bounded. And what you should be thinking about is that this is replacing a homomorphism. This was an honest to goodness homomorphism. If there was no twist in the action, then H would be a homomorphism. Okay? And if you look at the variance of a homomorphism, that's exactly the second moment of a martingale. So you start getting things which are very, very convenient. Okay? This is very close to martingale theory, and this is part of the intuition why you want to look at these harmonic cocycles, because it's kind of, okay, not exactly a martingale, but almost there, right? Almost there. And in fact, H is a martingale, right? You're looking at squares of martingales. That's nothing more than that. Okay? So let's check what this is. Okay? So this is equal to, very careful. This is equal to the expectation starting from x of hv xt, all of this squared, minus, well, I'm going to write it this way, h of x squared. I start writing the v and so on. Right, because this is the square of the expectation. H is a martingale. H of xt is a martingale. Okay. I need to analyze this thing. Okay. What is this? Well, this, stop, I'm not writing the v's anymore. This is inside, okay? Inside, square is inside. What is this? This is what? Well, it's expectation of C of xt, inner product with V, absolute value squared. You can write this also as V inner product C of xt. You agree? Complex number times its complex conjugate. Wait, there is a form, there is an alternative form where I can write this thing. Okay? Any two vectors I can write in this way. This is C of xt tensor C of xt. This is some random Hilbert-Schmidt operator. Okay, right? Inner product with V tensor V. This identity is a pointwise identity. It's always true. I gave it to you as an exercise. If you take two tensors, basic tensors, and you inner product them, then you get the first component with the inner product of the first component and the conjugate of this, and then the reverse direction with the other. What's the definition of the inner product? This is, well, yeah, this is one way to define the inner product. We define the inner product by summing over an orthonormal basis, but you can see that this is just the same. This was an exercise after we defined what the inner product. The inner product we defined to take an operator, because this is only a good definition for basic tensors, and then you need to kind of extend it. We defined it, the inner product as you take an orthonormal basis, and the inner product is you act with your two operators on the orthonormal basis, take inner product of that and sum everything. And but if you check that, right, because you can decompose this on an orthonormal basis and decompose this one on an orthonormal basis, and then you get, right, you get two sums, and then these things become exactly what's really. Okay? It's just a true fact, and if you don't remember it, you can recheck it for yourselves. Okay, so now I need to analyze what is this guy. So let's write it down, see what happens. Now you have to be careful because CXT tensor CXT, this is not a harmonic object, right? Because I have a tensor, right? I cannot sum each coordinate separately, right? Like should imagine it like if you take the product of two linear things, right? That's no longer a linear thing, right? If you take two linear functionals and you take their pointwise product, that's not a linear functional anymore, right?
Now you can ask the question, why is this the variant? Isn't there supposed to be a
So
The expectation
this is
of-
the variance because it's the expectation of the square minus the square of the expectation. The expectation, this is HV at x0. Because it's H is a harmonic function, it's a martingale. That's just going to be a correction term at the end, you're going to see. Okay? In fact, Ozawa wrote it with expectations and without variances. But I think if I remember correctly, I might be mistaken, I don't want to. Record.
About the last equality, didn't we say that the inner product of two tensors is taking the inner product of the first coordinate with the first and the second with the second?
We said this in,
That's what I said. So
Yes.
I defined
Yes, but it's the other way.
the inner product, I defined the inner Hilbert-Schmidt inner product. Summing over an orthonormal basis and taking AB inner product A tilde B. Okay, this was the definition of the inner product, where this sums over an orthonormal basis. Any, to show that it's not. Then I gave as an exercise, once we define these things, that U cross U, in fact, U cross U tilde, V cross V tilde, okay, any four vectors, this is U, V, inner product of V tilde U.
I just mean that
This is what I'm using here.
in the second line, the other
yeah.
term is VCXT and not the other way around.
but look how we defined it.
Oh, so it was, okay, okay. Now it's okay.
I didn't change anything. I don't know how it became okay, but it's okay then good. Is
Yeah, because I thought it's the first coordinate with the first coordinate and the second with the second.
no, but you have to check that this is what happens.
Yeah.
This is because when you act, you have to move to, okay, you have to check that this is the way it goes. I might have gotten confused here. Is this what your problem? That it should be U tilde V and then V U? I might have written.
He thinks it should be UV, U tilde, V tilde.
No,
Just
so
put conjugate.
one of them has to go in the other direction.
Yeah.
One of them has to go in the other direction. It comes from the fact that if you want to take U and V, then you can sum them over an orthonormal basis and take
Yeah.
UB, BV. This goes in the other way.
Yeah.
Right? So bracket. Right? This is and now I'm worried, okay, now I'm worried that maybe there's a complex conjugate on this thing. One of them, they don't play the same role. Right?
Suppose
Left side and right side are different things. These are functionals, these are vectors. So now I have a suspicion that I actually reversed the actual numbers that are written here. But go do the exercise and tell me what it is, okay? And then, but here it doesn't matter, right? Because it's symmetric. So I mean, even if I was supposed to write it as the complex conjugate of
The
this.
conjugate of an inner product is also an inner product. So it doesn't matter.
No, then it's antisymmetric. It's not antisymmetric, it's
Not
the
linear.
scalars don't come out right. They come out conjugated in the first coordinate, so you have to be careful.
I mean, you can choose in which coordinate you want it to be conjugate and in which not. You can want it in the left or the right. Okay.
Okay, it's in this case, this is a real number. The way I know it's a real number is that when you have UUVV, right? Then you get something times its conjugate. So it's a real number. So complex conjugating this thing is not a problem. So here I know that I can write them in any direction, okay? If you had general four vectors, then there is some conjugation to be done and you have to, complex conjugation to be done and you have to be careful that you're doing it properly, okay? But we're getting bogged down in details of covering the real story. So the real story is, I was trying to analyze this variance. I said, okay, there's some constant term, I put it on the side, right? Or you could imagine that I've taken x equals 1. This will be enough for what I'm going to try to prove, okay? I could take x equal 1, it's not important. If I took x equal 1, then that term would be 0 because C of 1 is 0, right? So, so I only need to analyze the square, the second moment. To analyze the second moment, I realize that I have an inner product times its complex conjugate, which is exactly the tensor. This is what leads me to say, oh, let's look at the Hilbert-Schmidt space. So So now I want to analyze this guy. Where does this live? It lives inside the Hilbert-Schmidt space. Random operator inside the Hilbert-Schmidt space. It's a function from omega to the Hilbert-Schmidt space, measurable in the correct sense, which gives me, for every little omega, it gives me some operator. Okay? Now,
This is a random operator.
it's right, because this is random. So you need to plug in an omega here to say what the values are, but for every, tell me where you are in the random walk, I give you an operator. Okay? Now, what happens if I want to understand the average of these things? Okay, I want to understand the average of these things. Okay, so we want to basically develop AT in terms of AT minus 1. Okay, so let's take T strictly greater than 0. I want to develop AT in terms of AT minus 1. Then we can write XT as XT minus 1 times U, where U and XT minus 1 are independent, right? And U has law, same law as X1, or mu, right? The distribution of the next step is mu, right? This is the, U is like the UT, right? I multiply by an independent element. Okay, so that's just a notation, I'm just giving them names. Okay, so let us write what is C, what is AT? I already have the notation. What is AT? AT is equal to the following. It's equal to C of XTU, XT minus 1U, XT minus 1U, tensors. So I'm going to write XT minus 1U. How do I write XT minus 1U? C of XT minus 1 plus XT minus 1 acting on C of U. Right? This tensor with itself. Do you allow me to do this? Can I do that just to save
Go for it.
save the department's marker budget? Okay? Can we do this? I mean, it makes I really appreciate this notation because I think it makes everything so much easier to read. But you just have to remember that the two parts of the tensor, they come from the same space, but they don't really come from the same space. They're like playing, one is functionals, one is. But anyway, okay. Okay, so we have this tensor with itself. Now, how do we open up a tensor with itself? You have to be careful. We didn't do this. I didn't do this, but maybe I write this. This is a basic exercise in tensors. Tensors are linear. Okay, we didn't prove it, but we kind of defined them. We kind of define tensors as Hilbert-Schmidt operators. You can go the other round. You can define what a general tensor product is, and then find out that tensors span the Hilbert-Schmidt space. But when you take this this kind of object, then it's linear in both coordinates. Right? It's linear in both coordinates, and even though you can get different, the scalar can go in and come out of the two coordinates simultaneously. Okay, so this is what a tensor is, and so I can open up this linear. So what do I have? So I have this with itself, tensor with itself, right? Just like a product. And I have this with this. Then I have this with this, right? And then I have this with itself. Okay, so I get the following. I get C of xt minus 1 plus C of xt minus 1. What is that? 80 minus 1. Okay. Plus C of xt minus 1 tensor xt minus 1 acting on C of U. Right? Plus, I'm going to write it here on the bottom, xt minus 1 acting on C of U tensor with C of xt minus 1. Okay? These are the two cross terms. Plus xt minus 1 acting on C of U tensor with itself. Let me do the squaring. You agree? It's linear. What am I gonna do now?
Xt is acting by unitary, so.
Yeah, xt is unitary, right? So first of all, I'm gonna write a few things. Okay, let's erase it. You can remember the quality. What am I gonna do now? Going to, so what did we get?
And C of U is 0.
AT, we can sum AT over U U indicator U is U. Yeah, I mean. I want to average over, I want to take expectations. Okay, so I could have also. So I want to average over this guy, over U. Okay? If I take the average over U of AT minus 1, of AT, right? So I sum over all U. I look at the probability that U is equal to U. What is this? This is just U of U.
Yeah.
Right? And here I put the AT minus AT. Okay, where AT is a function of this specific U. I mean, okay, so I plug in and you understand what I mean, right? So I'm writing like this.
What is this calculation?
I'm just averaging this equality over the U's. Okay, I'm averaging it over the U's, over the actual values of U.
Averaging in.
Just averaging, right? What do I get when I average? I get one term which does not depend on the average, which does not depend on U, it's just AT minus 1. Or just average a fixed vector in the Hilbert-Schmitz. It's a fixed operator. Then, let's see. When I average these over this U, then everything is linear, right? This is I bring in the average into the second component here. I bring the average into the action of xt minus 1 because it's, right? And they're independent, so I mean, this is why I can average. But when I average this, I take expectation only over this capital U, then I'm just averaging inside here, right? And what is the average of C of U?
0.
0, because it's a harmonic cocycle. Exactly the average around 1. Same thing here. This is in the first component, get a linear. So these two terms fall off. And what is this? When I take the average over U, this is just the average of A1. In law, this is the same. Yeah, sorry. I need the XT. I need the XT. I need the XT. You have to be careful, okay? So this is just the average. U. I'm going to write it. U of U, the second term, U of U, of what? Of X. So now I'm reminding you that we had another exercise that said if you act with the X on both coordinates of a tensor, then it's the same as conjugating by the X, the original tensor. Right? You just compute what the operators do and they both do the same thing. So, so I'm using the fact that this is conjugation and I have xt minus 1 composed here. And in the middle, I have a tensor. Which tensor? Cu tensor with itself. Right? Because this is the same thing as acting here, and then taking tensors. Okay? We had this on the board at some point today. Okay? Now, this conjugation is, again, these are linear operators. I can pull them out of the sum. So I have the average of Cu. What is the average of Cu? That's the average of A1. In law, it's the same thing. Right? So now I can define A tilde. This is no longer going to be a random Hilbert-Schmidt. This is going to be an actual Hilbert-Schmidt operator. Okay?
Why this A1?
I mean, just going over all the U's, this has the same value as A1. Same distribution as A1.
What is CX1, X1, and X1 has the same distribution of U.
Okay? So again, I'm going to define A tilde of T. This is going to be by definition. I want to average, I want to do this. But wait, what is this? What is this? This is expectation over what? Over random walk, over a Hilbert-Schmidt operator. So let me spell it out. So I put this in quotes because we never defined expectations on Hilbert-Schmidt operators. In fact, we never defined the expectation on vectors, like even finite dimensional spaces. But what I mean by this is that I sum over all possible x take the distribution of the correct thing you want to plug in there, which is mu to the tx, right? You want this is the probability that xt is equal to x, okay? Times what? Times the actual vector that you want to get here, right? So this is xt with itself. This is the AT, right? So this was my motivation. I played around with the AT. I saw that if I average
So,
things,
X, right?
it X, yes. Okay? So this is exactly this is what I would expect to be the average operator of the ATs. And this is what I call AT tilde. AT tilde is already the average.
Plus C of 1.
No. I just defined the average of these operators.
The
convex combination.
The average has some error term.
Each one of these is a term like this, and I average over the XTs to get a fixed operator. Just some number. It's the barycenter of all these operators. Okay. So now, but what does this give me? So I get an equation, right? I get an equation A tilde T. This is the average. Okay, but if I do that computation that I just did over there, what I get here is that this becomes, well, I can sum this over x and over, so now let's maybe do it, I sum it over y, I sum it over u, and then I do the probability that xt minus 1 is y times the probability that u is u. You agree that this is the same as this, right? Same thing, if I think of x as being y times u, right? So same. Then here I take c of x, y times u. Tensor with itself. Now, if I fix the y and I average over the u, right? Then I get that harmonic computation. Maybe I should have presented in them just with fixed values, but anyway.
No, you move to a double sum?
Yeah, so now I bring the sum.
The motivation
the sum
and
over u. Now I bring the sum over u inside. I do the same computation that I did there, but with fixed.
Probability of u equals u, right?
This summing over all of this is exactly summing over all of this.
Right.
Times the correct element. I just wrote mu as a convolution with itself. Mu to the t is mu to the t minus 1 convolution mu. That's what I did. Okay? And now I sum over this. I get this. Right? And on the inside, what I get here is we said the cross terms disappear. It's the same computation as I did over there. The cross terms disappear because of the harmonicity around 1. And what I'm left with is one term, which is cy squared, and another term, which is y minus 1, conjugating what? Conjugating cu squared.
Don't we know?
I need the average. I need the average. I have to be careful. So it's y conjugating sum u of u. Okay? Or probability that we can change this to be probability x1 is u, right? And then we have c of u squared, and then y minus 1. So all of this is inside the conjugation, right? Because I brought all of the sums. I brought the sum over u into the linear operator. Okay.
Once again, if we enter this sum to the tensor, doesn't we get 0?
No, because you cannot average both coordinates at the same time.
No, exactly. I'm not doing it. I'm doing in one coordinate, and then I have.
You can't. The other coordinate also depends on you. If you have, imagine you have this v times 1/2.
Yeah.
U times u.
U is not fixed. Okay.
I cannot write this as half v plus half u tensor, right?
No, yeah, I got it. Sorry.
It's a square. It's not a linear.
In the other case, then we will get 0.
What?
Here we got 0 because xt minus 1 was always fixed, right?
So what you should imagine is you're averaging over xt, but you can split that average into the average over xt minus 1 and average over u. U is independent from xt, so the average over u pushes inside, kills the cross terms, and you're just left with the two others.
Yeah,
Okay.
because
And this is exactly this computation. Okay? But this, by definition, this is exactly A tilde 1. By definition, this is A tilde 1. That's what I said, A tilde T is the average over the Tth step, this is the average of the first step. Right? By definition, this average is A tilde T minus 1. Okay? So I just proved that A tilde T is A tilde T minus 1 plus what? Averaging over Y's
Where's A tilde?
I completely did it wrong. Okay, what I'm writing is going to be true, but I'm going to have to do it again. This is what happens when you explore and you don't, well, maybe it's a good lesson. I mean, we explored a bit and now we'll find out something nicer. Okay. Do it again next time. So this is A tilde T, is A tilde T minus 1 plus, what did we get?
Expectation
We
of
got
A1.
sum over all the Y's, we get probability that xt minus 1 is y, or mu t minus 1 of y,
A1 tilde.
right? Of y conjugating A1 tilde. So the way, what happened was that we wrote, okay, so I'm going to tell what we're going to do tomorrow because I did it wrong. Maybe it's actually good this way because we kind of see, okay, we do the first natural thing, and then we say, oh wait, I need it in the other direction. Okay? I'm not claiming that this was planned, but we can imagine it was. So I get an equation for AT tilde, for AT tilde, in terms of AT tilde minus 1, plus what? Plus some average of some operators acting on A tilde minus, or A tilde 1. Average of linear operators is a linear operator. So I've written AT tilde is equal to AT minus 1 tilde plus some operator T,
Depends on theta.
which depends on T minus 1. That's the problem, okay? Acting on, so this, where is this operator living? This is already an operator living in the bounded operators on the Hilbert-Schmidt space. So this is one more level. This is already level 2. Okay? It's already on the second floor. Okay? So this guy acts on A1 tilde. What I want is this operator to be constant. If I get a constant operator, not depending on the time, right? Not depending on t, then what I'm going to, so tomorrow what we're going to do, we will actually decompose it the other way around. We will write xt as an independent variable times something that has the same distribution as xt minus 1, not the xt minus 1 from this random walk, but some t minus 1 steps. Okay? And if we do it that way, so tomorrow we'll do the whole computation again. I'll do it tomorrow. So tomorrow what we're going to do is we're going to do A tilde t, and we're going to decompose it as AT. Okay, so we have to be careful. So how are we going to decompose it? We're going to peel off the first step. The first step will give us an A1 here. Without anything, it will be the first term, right? Exactly like we did here. And then the second step will have to have this conjugation by the first step. But then that doesn't depend on time. It's just conjugation by one specific thing. So we'll have a T, which is going to be a bounded operator in the Hilbert-Schmidt, on the Hilbert-Schmidt space, okay, acting on AT minus 1 tilde. Okay, what is T? T is exactly going to be the operator which takes a Hilbert-Schmidt operator, call it A, right? And averages all the x's and does xa, x minus 1, right? Do you agree that this is a linear operator, right? This is the linear operator on the Hilbert-Schmidt space. Okay, so this is exactly going to be T. So this is what we're going to get tomorrow. But you see, if you continue this, you get that A tilde T is what? Is the sum from 0 to T minus 1 of T to the K to the jth power, right? Applying T. Every time you apply another T, right? This is a linear operator, so you get another one to A1. We have a fixed vector and a Birkhoff sum, right? So the ergodic theorem screams, let's use the ergodic theorem, right? I mean, divide by T and see what happens, right? But then this is this one, which had to do with the variance. So you get something about the variance divided by T. You get information about the variance, and this is going to converge to something that we can maybe analyze. And you see where everything just pops out naturally. I mean, I know that I taught you the ergodic theorem, and I taught you the invariant vectors, and I taught you things like that. but I presented them to you. You should imagine that you have someone sitting in some place in Japan or somewhere, and they have this all in their head. So they're just looking and playing with the harmonic function, and it just pops out naturally. There's no reason to. I mean, my suspicion, what I would have done first would have done this. Then what I would have noticed is that if I did it the other way around, which is the same exact computation, just doing it, again, which is what we'll do tomorrow, I would get an ergodic sum. So I can apply the ergodic theorem. The most basic ergodic theory. It's not even like any sophisticated ergodic theory. Okay, so this is what we'll do tomorrow. Tomorrow we start from scratch. We do it properly, define the A tildes. Maybe we call it tomorrow AT just to make.
Did we talk about the ergodic theorem?
We proved the ergodic theorem. Von Neumann ergodic theorem.
Oh,
Right?
right.
We gave a proof of the Rees proof of the von Neumann.